Welcome to The Explainer. Today, we're going to pull back the curtain on the single most important piece of software running on your computer, the operating system. It's kind of like this silent magician that makes everything you do, well, possible. So let's just start with a really basic question that gets right to the heart of things. You've got this powerful processor, you've got all this memory. Why not just let your web browser or your video game talk directly to the hardware? I mean, it seems like it would be simpler, right? Why have a middleman?
Well, it turns out that would be an absolute nightmare. Seriously, our computers would be incredibly clunky, they'd be stuck doing only one thing at a time, and every single program would need to know the super complex details of every piece of hardware inside. So the OS steps in. It acts as this brilliant intermediary, this illusion factory that makes all that complexity just disappear.
So, here's the plan for today. First, we'll look at the big picture of what this great illusionist really is. Then, we'll dive into how it juggles all your running programs. After that, we'll see how it shares the processor. Then pull off the infinite memory trick. And finally, we'll see how it organizes and protects your entire digital world. Okay, so first up, the great illusionist. What does this master resource manager actually do? Well, it really has two main jobs. First, you can think of it as a translator. It takes the messy, complicated language of raw hardware and presents this really clean, simple version to all of our applications. And second, it's like a tough but fair referee, making sure every single program gets its turn with the computer's resources, like the CPU and memory. And to do all this, the OS performs three incredible magic tricks. First, it creates the illusion that you can run your browser, your music player, and your word processor all at the exact same time. It's amazing. Second, it makes each of those programs feel like it has the entire processor all to itself. And third, it gives each program the sense that it has this huge private memory space, way bigger than the physical RAM you actually have installed. All right, let's get into that first illusion, multitasking. How on earth does your computer juggle dozens, maybe even hundreds of tasks at once without dropping a single one? Well, the secret starts with something called a process. Now, what's really important to get here is that a process isn't just the code for an application. No, it's the application in action. The best analogy is to think of a chef working in their own private kitchen. They've got their own ingredients, their own stove, their own tools, and the OS makes sure that one chef can't just wander into another chef's kitchen and start messing with their stuff. And what's fascinating is that a process is constantly changing what it's doing. It isn't always running. In fact, most of the time, it's either in the ready state, just waiting for its turn on the CPU, or it's in the waiting state, paused because it's waiting for something else to happen, like for you to type on the keyboard or for a file to download. And the OS scheduler, it's the master conductor of this whole dance. Okay, now let's go one level deeper. Inside a single process, you can have multiple threads. So if a process is the kitchen, then threads are all the different chefs and assistants working together inside that same kitchen. They all share the same ingredients, that's the memory, but they can work on different parts of the meal at the same time. This is exactly how your web browser can be downloading an image with one thread while you're still scrolling the page with another. It's all happening in parallel. So this brings up a pretty big challenge, right? If every process is stuck in its own private kitchen, how do they ever talk to each other? Well, that's where inter-process communication, or IPC, comes in. They have two main options. They can pass messages through the OS, which is kind of like sending sealed letters. It's super safe and orderly, but it can be a little slow. Or the OS can set up a shared whiteboard, a common chunk of memory where they can both read and write. This is way faster, but they have to be really, really careful not to scribble over each other's work. All right, on to the second great illusion. You probably have one processor, maybe with a few cores, but you've got dozens of processes and hundreds of threads that all want to run right now. How does the OS make every single one feel like it's the star of the show, with the CPU all to itself? This is a great way to think about it. The CPU is like that one incredibly fast checkout clerk in a super busy store. All the processes are the customers lined up. The scheduler's job is to figure out which customer gets served next and for how long. The whole goal is just to keep the line moving smoothly and try to keep everyone happy, which, as you can imagine, is a pretty tricky balancing act. So to manage this queue, the scheduler uses different strategies. Some are really simple, like first come, first served, just a basic line. But that can get slow if one huge job holds everyone else up. Others try to be smarter, like shortest job first, kind of like an express lane. But the one that really creates that feeling of seamless multitasking is round robin. It gives every single process a tiny, tiny slice of CPU time, and it switches between them so fast that it feels like everything is running all at once. Okay, this next trick is, and I'm not exaggerating, pure genius. Every single program on your computer acts like it has gigabytes and gigabytes of its own private memory, even if you only have, say, 8 or 16 gigs of physical RAM. How in the world does the OS pull this off? This is the magic of what we call virtual memory. Here's what happens. The OS gives each process a map to a giant imaginary mansion of memory. It's huge. But in reality, the OS only loads the rooms of that mansion that the process is actually using right now into the real physical RAM. The rest of that mansion? It stays packed away on the much slower hard disk, waiting until it's needed. So, how is this whole trick managed? It's a system called paging. The OS breaks that program's imaginary mansion into these equal-sized chunks called pages. Then it breaks up the actual physical RAM into the exact same sized slots, and we call those frames. The OS then keeps this master map, called a page table, that tracks which page from which mansion is currently sitting in which frame of RAM. It's a massive accounting job. So what happens when a program needs a part of its mansion, a page, that isn't in RAM at the moment? The hardware triggers something called a page fault. Now, fault sounds like an error, but it's not. It's totally normal. It's just a signal to the OS that basically says, hey, I need you to go find this page on the disk and load it into an empty frame for me, please. This is the core mechanism that makes the whole illusion work on demand. Okay, so all of these illusions we've talked about come together to manage our most precious resource, our data. So for our final trick, let's look at how the OS turns the physical chaos of a storage drive into the nice, organized library of files and folders we use every day. You know, a file is another one of these beautiful abstractions. We see a little icon for a document, but the OS sees so much more. It organizes files into directories, sure, but it also tracks all this metadata, information about the file, like who owns it, when it was created, and its size. And it handles the translation, using things called device drivers to turn our simple save command into the complex language the physical drive actually understands. And just like with the CPU, when a bunch of programs all want to read or write to the disk at the same time, the OS has to schedule those requests. A really common strategy is the elevator algorithm. Basically, the disk's read/write head moves across the disk in one direction, servicing all the requests in its path, just like an elevator going up and servicing floors, before it turns around and goes the other way. This stops it from jumping all over the place inefficiently. Finally, let's talk about security. Because all of these mechanisms we've discussed, isolating processes in their own little worlds, managing who can access which files, controlling the hardware, they aren't just for efficiency. They are the fundamental security model of your entire computer. The OS is your ultimate gatekeeper. It creates all these layers of defense. It starts with user accounts to know who you are. It uses that process isolation we talked about to build these strong walls between programs. That's why a crashing web browser usually doesn't take down your whole computer. It sets file permissions to control who can see your data. And most importantly, it separates itself into a super privileged kernel mode, which stops regular apps in user mode from doing anything truly dangerous to the system. So when you step back and look at it, the operating system is just this masterpiece of abstraction. It's a silent illusionist that's constantly managing this immense complexity just to create a simple, powerful, private little world for each of our applications to live in. It's the foundation for everything we do. Which leaves us with one final thought to chew on. If the OS creates this perfect world for every app, what does it take to protect that world? Not just from other apps, but from flaws within itself. Thanks for watching.